my friend Rhett was modeling this really cool problem of an inverted pendulum where the pivot point is driven by a sinusoidal drive, just vertically up and down. And every time I had seen this online, YouTube videos of it, I had assumed there was more to it than just simple modeling the pivot moving up and down. So I was so excited about the work that he showed. So I wanted to see if I could do it with Lagrange multipliers, because that's what I'm always testing myself with. And then I wanted to see what would happen if I did it in 3D. So I have an amplitude of 0.1, a length of the bar that's going to be roughly 1. You'll see why it's not exactly 1 in a second. And Rhett is the one who showed me that you really need to kick your angular frequency up for the driving of the bottom pivot point. So I was starting with really low ones, and the pendulum was just falling over and just being a regular pendulum down below the pivot point. So my pivot just moves up and down, a times the sine of omega t. The other point is just arbitrarily x, y, and z. The constraint is that the distance between the pivot point and the point we care about has to be held fixed. Now, if I square rooted this, that would be the length, but who cares? If the squared length is maintained, that works out the same. So the kinetic energy is just r dot dotted into r dot. That sounds funny. And the potential energy is just mgh, where the height is z. The Lagrangian is t minus u. And so what I'm doing is this Lagrange multiplier here. So you take the derivative of the constraint with respect to the arbitrary variable. So the differential equations that I need are the Euler-Lagrange equations for x, y, and z. I need to have the constraint 2 time derivatives. I have a whole other video about why you have to do that, set equal to 0. And then what I'm doing is 2 things. I'm setting it to be just a little bit off to the right. X is not 0, but y is 0, and z is up at r. So really the length of my bar is the square root of 0.1 squared plus r squared. So a little bit bigger than 1. You'll see what it is when I plot it. And I don't have it moving in the x direction, because if I did, it would just grow the whole time. I do have it moving in the y direction, though. Quite a bit of motion, actually. This is really kicked, it's like smacked over to the side with a very high velocity here. And then I need the z to just be moving up the same way the pivot's moving up. Otherwise, my bar wouldn't stay the same length, because that's, if you do this trick here on this line, you have to be very, very careful with your initial conditions so that the constraint doesn't grow, because really all you're telling it is that it can't accelerate, but that means that it could grow. So you have to be careful with that. And so I just ran all this already. And here's a plot of the constraint over the full time, and you can see that we're really zoomed in here. So it's working hard to try to keep the constraint, and it's doing a pretty good job out to at least 1% here. Better than that, it looks like. It's really this digit here. So what is that? 0.001%. So it's doing a great job. So here is a movie of it happening here. So I'll just get it to play right where it is now. So what it does is x is this way, y is out towards us, I believe. No, I can't remember which way is which. But it just kind of oscillates up and down, and sure enough, it's stable above. The red is the pivot point, and the black is really staying stable above, which is super, super cool. I'm so glad Rhett pointed this out to me.